So in this video, I'm going to go through a quick recap of what final value theorem is, and then we're going to do an example. So the final value is the system output at time is infinity. So you run this system all the way to the end of time, and you figure out what its output value actually is. So there's an equation that we can apply for this, which involves the limit as t goes to infinity. And for this, we need to use our output function as a function of time. So that's what the t in here means. Now, if you're working in the S domain or the frequency domain, you can also apply final value theorem, except we're going to be looking for the limit as S goes to 0 instead. And we need to do it for S, our Laplace variable, multiplied by f as a function of our Laplace variable. So that's your two different options. Usually, it's going to be easier to always apply the S version of the equation if you've already got your transfer function in terms of S. Otherwise, you have to perform the inverse Laplace transform to get back in terms of t, and then substitute in t as infinity. So let's go ahead and perform an example. And I'm going to try and find the final value for the system when the input to it is a unity step. So what that means is our input, so this is our system, the input to the system is r of s. Now remember, this is just meaning it's a function of s, so I'm going to drop it. And it's going to be equal to 1 on s. So a step is 1 on s, and unity just means that the input is equal to 1. If you had a step input of 3, then you'd need to multiply this by 3 instead. So let's go through and figure out what our c is going to be at the end of time. So I'm going to do this in the S domain, since we've given our transfer function in S, and then I'll show you what it looks like in terms of t as well, just to show that they're going to get the same answer, just that this is the easier route. So the final value for our system is going to be equal to the limit as s goes to 0 of s times the output to our system. So that's going to be c in our case. And again, I'm going to drop the little function of s thing because it doesn't really add anything to the system. And it gets a little confusing to know whether this is a function of s or what an actual s, as in this case. So we know that for our system, the transfer function here is going to be c divided by r. It's going to be this here. Okay, but what we actually want is the output c on its own. So we can multiply r up to the other side. And we can substitute in, we know it in terms of s. Okay, so this is what c is in terms of s, and we can now substitute that back into our limit. Okay, now at this point we need to make sure we can cancel everything that can possibly be cancelled. So s on the top line is going to cancel with the s on the bottom line here. It's nothing else that we can really do. So now we need to substitute in our limit, and that's s going to 0. So we're going to get 1 over 3 times 0 is 0, 2 times 0 is 0, 1 remains on its own. So we get 1 over 1, which means that our final value is going to be equal to 1. And that's the answer that we were looking for. Now, if you have access to Matlab, you're able to actually check whether this is correct. So if we go through, I've written myself a quick little function that applies a step input to my transfer function. And this here is the output that I get from that. And what we're interested in is the final value. So that's going to be the steady state value at the end of time. So it puts up a little marker for us. And if we click on that, we can see that it agrees with us that the final value of our system is going to be equal to 1. So let me just quickly show you that this will also work if you go ahead and inverse transform our equation. So this is what we said c as a function of s is. This one is going to be the function of time, if we quickly pop those in. So this is of s, this is of t. So I've just got this out of Wolfram Alpha. I haven't bothered to actually do it manually. But what we need to do is, we know that we can find our final value from using the time version of the equation if we just substitute the limit when t goes to infinity. So final value. So if we go ahead and put this in here, 1 isn't going to change. And I just realized that I drew this wrong. It should just be over this bit. Okay, so the 1 isn't going to change. That just stays there. And if we substitute t is equal to infinity into this stuff, well, the first thing that we have is e to the power of negative infinity on 3. So as e goes to the power of negative anything big, it's going to approach 0. And when it's infinity, e to the negative infinity, that's actually just equal to 0. So if this here is equal to 0, everything else, it doesn't even matter what it is, it's just going to be 0 as well. So we're going to get 1 take 0, and this is equal to 1, which is exactly the same as what we had before, except using the easier version, which is when we're in the S domain. Okay, so that's all there is. See you in the other videos.